question is, if we start with 10 grams of hydrogen and we convert it into water, how much energy is released? And it gives you the delta H, and it says that's negative 483.6 kilojoules per mole. So the reaction that produces water, we'd have hydrogen gas, we'd have oxygen gas, because basically what you're doing is combusting it or burning it, and you're getting water. You show that as either a liquid or gas. Depending on certain conditions, you could do either one actually. To balance the equation, you should use an atom inventory, but this is pretty simple. Okay, that's really how you balance it. I'm not going to show the atom inventory just because it's pretty simple, because I wasn't asked about that. Yep. There's a 2 here? Yeah. And here? Oh, right, you're right, all right. So I'm sorry, and I said it was simple, didn't I? All right, so, what? I know, I should have done the atom inventory, shouldn't I? Okay. So 10 grams of hydrogen, we're converting it to oxygen. The enthalpy of the reaction is, the enthalpy change for the reaction is negative 483.6 kilojoules per mole. Balanced equation. And so we're going to start, when we're doing the stoichiometry, with 10 grams of hydrogen. And we got to convert it into moles because our energy is in moles. Or I guess we could convert this into grams. Doesn't really matter, I suppose, in the long run, but the way I've taught you to do this is to convert that into convert this into moles. So we got 2 hydrogens, 1.008 times 2, 2.016 grams of H2 equals 1 mole of H2. And so from this equality statement here, I can build a conversion unit here, 1 mole of H2 and 2.016 grams of H2. And I put grams in the bottom so that I can cancel grams. Okay, and so what we're going to do is do this multiplication or this division, and we're going to end up with the moles of H2. Now, this is per mole. If we include this in the equation, it becomes just kilojoules, but since we've got 2 moles of this, we have to multiply this amount by 2. Or conversely, we could divide all the coefficients by 2 and just plug that number into this. This is what's happening in the system. If we put it in the equation, it's what's happening in the surroundings. So while it's a negative term here, you reverse the sign here. Does that make sense? Yes? All right. So we can do this one of 2 ways. We can include it in the equation and make that a positive sign times 2 because we got 2 moles of this. That's 12, carry a 1, 6, 7, 16, 8, 9, 986.2 kilojoules. Okay? So we don't need to have per mole here because it is for 2 moles now. All right, that's one way to do it. Another way to do it is to divide all the coefficients in the problem by 2 and just include this number, reverse the sign. So let's do that. Let's show that as H2 plus 1/2 O2. And combustion reactions are the only occasion where you can use fractional coefficients. Oh, that should be an arrow, H2O. Okay. And then we're going to include the actual number there. The negative 483.6 kilojoules per mole becomes positive because when it's in the equation, we're talking about what's happening in the surroundings. The delta H term is what's happening in the system. This is what's happening in the surroundings. So in the surroundings, we're going to get this amount of energy out. And if you're applying a reasonableness test to this, it should make sense because I hope you know this produces heat. Okay? When they were launching rockets to the moon, those rockets were fueled by hydrogen fuel. Okay? They produce energy. There's something called a hydrogen fuel cell. South Carolina is really big in the hydrogen research community, producing hydrogen fuel cells and trying to make them more efficient. So they're producing energy. We want to use that energy then to drive cars and things. So it's important that you kind of know some of this stuff by common knowledge, all right? Now, remember, the reason the delta H is negative here is because what we have is, in the system, energy is leaving the system. The system is wherever the chemicals are. It's the actual chemicals themselves, the bonds between the chemicals, the reaction between the chemicals. Okay, any action between these individual particles. That's the system. If I were running this reaction in water, and you can't run this reaction in water, but if you were running a reaction in water, water is not the system. Water is the surroundings. Okay? It's just the chemicals that are doing the reacting, or the chemicals doing the changing that are the system. And then anything around that makes up the surroundings. Okay? Surroundings. Okay? So delta H is what's happening in here. And if we're moving energy from here to the surroundings, as we are with this reaction, then the energy in the system is going down, and the energy in the surroundings where we are is going up. So it's going up here because this is talking about the surroundings. It's going down here because that's talking about in the system. And all of this together, surroundings and system, make up the universe. Okay, the surroundings are everything outside of whatever the system is, up and including Alpha Centauri. Okay, y'all know what Alpha Centauri is? It's the nearest galaxy, or is it galaxy or solar system? Solar system wrong? Anyway, whatever. It's the nearest solar system wrong. Nearest star to our own. Okay, or Alpha, there's another star that might be a little closer. That's the one they've often cited as being closest. Anyway, up to and including far-off galaxies. Okay, up to and including wherever. All right, the universe is made up of the system and surroundings. The system is what we're interested in when we talk about these kind of reactions. The surroundings is how we picture it when we're doing it, putting it in the equation itself. Either one of these two equations will work here. Okay, so if I've converted this already into moles, then I can take the 2 moles here and put it on the bottom, and this number put it on the top, or I can take the 1 mole here and put that on the top. Doesn't matter. Are you with me on what we're talking about here? Okay. So I'm going to choose to do the one on the bottom here. 1 mole, H2, and 483.6 kilojoules of energy. And we can cancel out moles, cancel out H2, and do the math. Okay, 10 times 483.6 divided by 2.016. I got 2398.8, so forth. Is that what you guys got? Just so I didn't be careful not to hit a wrong button. You should always do your math twice, just to be safe. And that's kilojoules. And then we need only 3 digits here. This measured number has only 3 digits. This one has 4, this calculated number has 4, this calculated number has 4, and only the measured calculated numbers are important for figuring out significant digits. You want to make your final answer have the same number of digits as the measured or calculated number. The problem with the least digits, this one has 3, the final answer needs to have 3, so we're going to get rid of a number in the ones place. And so to get rid of a number in the ones place, we've got to write down an answer in scientific notation. Remove the decimal place 1, 2, 3 places to the left. And so our rounded off answer then is 2.40 times 10 to the third kilojoules.